in the last session, I proved that if we have a graph and if the degree of every vertex is at most 2, then the graph can be decomposed into a bunch of connected components, and each of the connected components is either a path or a cycle. So after the session, one of you mentioned a nicer way of proving the same thing. So I'm just going to say it, and then I'm going to go to another problem. What we can do is we can look at the longest path in the graph. And let's say I have my longest path, V0, V1, so on, Vk. Right. Now we just do a casework. We ask, is V0 connected to Vk or not? So is there an edge from V0 to Vk or not? If there is an edge from V0 to Vk, then we have a cycle. And just like before, we can argue that this cycle is basically all of its connected components, because there cannot be anything outside of this cycle that has connections to anything inside this cycle, because then the degree of this vertex would be more than 2. But in the other case, if they are not connected to each other, they cannot be connected to anything else in the same paths, because that would increase the degree of that vertex to more than 2. And they cannot be connected to anything outside of this path, because that would contradict the fact that this is a maximum path. So then this means that the entire connected component is just this path. Okay. So in any case, we get that our connected component, our largest connected component basically is either a cycle or a path, and then we can remove that component and we can continue doing the same thing on the rest of the graph. Okay. Now, I want to prove something else. This is the first theorem for today. I want to say, suppose that all the degrees of the vertices in my graph are even. So in the graph G, we have that the degree of every vertex is even. I want you to prove that this means I can decompose my graph into a bunch of cycles. So my graph G is a union of cycles, and of course, I mean disjoint union here. So another way of saying this is that the edge set E of my graph, so my graph has vertex set V and edge set E. The edge set E is a disjoint union of some cycles. And let's say I show them with C1, C2 to CT. Okay. So let's do an example of this first. So let's say I have this graph, and the degree of every vertex is even here, and it's exactly one cycle too, right? So this is kind of a trivial example. But if I have something else, let's say I do something like this, and then maybe I do this, so the degree is 2. This one is 3 right now, so I just connect it to somewhere else. I'm really bad at counting. Okay, it was already 4. That was good. So this is 4. This has degree 2. This one has degree 3. So I just connect it to somewhere else, right? Now this one has degree 3. Yeah. It's too early in the morning. Yeah, this one now has degree 3, so I connect it to somewhere else. So this one now has degree 4, this one has degree 2, this one has degree 2. Okay. So I'm claiming that the edges of this graph are also a union of several cycles, right? And there are different ways to do this. So I can say, for example, take this cycle, this one, and this one, and they cover all the edges, right? But I could alternatively say, take this cycle first, right? And then take this larger cycle around it. this also works. Okay. So I'm not saying there is a unique way of doing this or that the number of cycles remains the same. I'm just saying as long as the degree of every vertex is even, there is at least one way of decomposing your graph into a bunch of cycles. Okay. How do you propose we prove this? We can do it by induction. And when I'm doing induction on a graph, what are the parameters that I can use for my induction? I can do an induction on the number of vertices. I can do induction on the number of edges. I can even do induction on the sum of vertices and edges. Right? So I can kind of define what I mean by the size of my graph depending on the particular problem. Now here, ideally, what I want to say is that I want to find a cycle, and then I want to remove that cycle and say that the rest of the graph can also be decomposed inductively, right? So if I'm just removing a cycle, I'm keeping the number of vertices the same. So I want to do induction on the number of edges. Okay. So here's our proof. We do induction on M. And I'm actually going to do strong induction here. So if I have no edges at all, of course, it's decomposed into cycles. It's decomposed into 0 cycles. So my base case where M is 0 holds. And actually, we don't have to do this, but let's just look at the case where M is 1. If M is 1, I have only one edge, and this edge is connecting 2 vertices. So these vertices will have an odd degree, right? So if M is 1, I basically have no graph that satisfies my assumptions. I have no graphs that have even degrees for all vertices and have only one edge. So in this case, my conclusion holds too, because I'm talking about the empty set, right? So technically, this is also correct. But in any case, for the base case, I just needed M equal to 0. Okay, so let's do the induction step. Okay, let's say that I have a graph, G, and it has n vertices and m edges. I want to somehow reduce the problem to the case where I have fewer than m edges, because then I can say by strong induction. So how can I do this? First of all, if I want to find the decomposition into cycles, I'd better be able to find one cycle. Right? So how do I find one cycle in my graph? Why does my graph have at least one cycle? Look, I don't even have the assumption that my graph is connected. Like, graph is this guy. But well, I can add that assumption, right? I can say, suppose my graph is connected, because if my graph is not connected, I can just apply the theorem to each one of its connected components separately, right? Just take each connected component, it's a connected graph, decompose it into a bunch of cycles. So I get the connectedness assumption for free here. So let's say G is connected. Okay. I'm not going to put it there because I want it to be. How do I find one cycle? Why do I have one cycle? Okay. Look, there are several ways we can do this. I can just say, let's do the walking on the graph that we did in a lot of our proofs before. I can say, start from your favorite vertex, X, and if it has degree 0, then that's it, because I'm talking only about a connected graph. So if X has degree 0, it's all of my graph, and the decomposition is just complete because I don't have any. Otherwise, this X is going to have degree more than 0, but its degree is even. So there is definitely a neighbor. So just walk to one of the neighbors. Now, when I get here, again, I have this situation where I already have one edge coming into this vertex, let's call it y, but I know the degree of y is even. So there should be another edge. So I can keep walking. I can go to some other vertex, z, so on, right? And every time I get to a vertex, I have used one of the edges that were connected to this vertex. And because the degree of this vertex is even, there is at least one other edge, I can keep going, right? But my graph is finite. So I cannot see infinitely many vertices. This path cannot continue forever, okay? So at some point, it has to go back to one of the vertices that I've already seen. And as soon as that happens, I have a cycle. Okay? So this is a very simple proof that we have at least one cycle. Okay. How else can I prove that I have a cycle? I'm just going to give you another proof. Of course, one proof is enough, but I just like to do this. What is a connected graph without cycles? A connected graph without cycles is a tree. And we've already proven that if you have a tree on two vertices or more, you have at least two leaves. But leaves are vertices of degree 1. So when I'm saying that the degree of every vertex is even, I'm saying that there are no leaves, right? Of course, this doesn't hold when you have only one vertex to that corner case separately. But if you have at least two vertices, then you will have two leaves. And that means that the degrees of all the vertices cannot be even. So if the degrees of all the vertices is even, your connected graph is not a tree. But what was another definition of a tree? And we had this equivalent definition that if it's connected and has no cycles, then it's a tree. We know our graph is connected. We know it's not a tree. So it has to have a cycle. Okay. So anyway, there is at least one cycle. So let's call this one C. We have a cycle C in our graph G. And at this point, I'm thinking of this cycle as just a collection of edges. It's a set of edges that forms the cycle. Now, what happens if I just remove all of these edges from my graph G? So I say remove all edges of C from G. And let's say that I call the resulting graph G prime. So G prime is the result of removing all of the edges of C from G. What can I say about this graph G prime? Well, the degree of every vertex in G prime is also even, right? Because the degree of every vertex was even originally, and then I took a cycle. Let's say this was my cycle. This is my cycle C, and the degree of every vertex was even, right? Maybe some of them had edges outside of the cycle, maybe some of them didn't. But in any case, I'm just removing the edges that appeared in this cycle. So I'm just removing these edges, right? But what does this do to the degrees of the vertices? Every vertex that is in the cycle loses two edges. So the degree goes down by 2. Every vertex that is outside of the cycle does not lose any edges. So before this operation, I know that the degrees of all of my vertices are even. After this operation, all the degrees will also be even, right? But now I have fewer edges. And remember, I'm still inside an induction. I'm doing induction on the number of edges. So now I have this graph G prime, which satisfies all the conditions of my problem. Basically, all of the degrees are even, and it has fewer edges than G. So by induction hypothesis, I can decompose G prime into a bunch of cycles. So just add C to that decomposition. That gives you a decomposition of G into a bunch of cycles. Okay. Great. Now, remember we talked about this problem that Euler solved, and this was like the beginning of all of graph theory in the city of Königsberg. So we can have a definition based on that. So we say that an Eulerian circuit is a walk that passes over every edge exactly once. Is a closed walk that passes over every edge exactly once. Okay. So imagine that I have a graph and I have a walk. I'm actually drawing the walk. And this walk passes over every edge exactly once. Where did I start from? I started from there, right? And it goes back to where it's. Okay. No, I didn't start from there. Where did I start from? Today I'm really sleepy. I don't know what's happening. Let's do this again. So I have a walk. This walk goes over every edge exactly once. And it goes back to where it started. Okay. This is an Eulerian circuit. And we say that a graph is Eulerian if it has an Eulerian circuit. Okay. So this is our next theorem. I want to say let G be a connected graph, because of course, if my graph is not connected, it doesn't really make sense to talk about Eulerian circuit. So let G be connected. I want you to prove that G is Eulerian if and only if all of the degrees of the vertices are even. So again, this is an if and only if statement. So we have to prove both sides. One side is pretty easy. So if my graph G is Eulerian, what does this mean? It means that I have a walk that goes over every edge exactly once. I have that Eulerian walk basically, and it's a closed walk too. It goes back to where it started from. So I say, take that walk. So let's say that V0, V1 to Vk is a closed walk covering all edges exactly once. So it's the Eulerian walk. Okay. And of course, V0 is equal to Vk. So what is the degree of a vertex in my graph? Every time a vertex appears in this walk, and again, this is a walk, so the same vertex can appear several times. But let's say at some point, I have Vi appearing here in my walk. So I'm coming to Vi from somewhere, and then I'm leaving Vi. So that's going to cover two of the edges that were adjacent to Vi, right? But I'm also assuming that my walk covers all of the edges exactly once. So if I have a vertex Vi, it's going to appear in my walk several times. I don't know how many times, but each time there is an incoming edge and an outgoing edge, right? So the number of edges of Vi that are covered in this walk is definitely even. But I'm assuming that the walk covers all of the edges of my graph. So the degree of the vertex Vi in the whole graph is even. And this holds for every vertex. So if my graph is Eulerian, then all the degrees are even. Now, let's do the other side. Let's say that all the degrees in my graph are even. I want to prove that this means my graph is Eulerian. And remember, I'm talking about a connected graph. I can use the theorem that I just proved before here, right? So I said that if all the degrees are even, I can decompose my graph into a bunch of cycles. And especially the way the decomposition worked was that I found one cycle, I removed it, and then I said I can decompose the rest of the graph, right? So let's see what happens if I do something similar here. So I find a cycle. Let's call this cycle C. Okay, this is my cycle C. And then I remove this cycle. When I remove this cycle, we've already seen that all the degrees remain even. But this doesn't mean that the remaining graph is Eulerian, because maybe the remaining graph is not connected anymore, right? So after I remove this cycle, I might have several connected components in the remaining graph. For example, let's say I have this connected component, and it has a bunch of other vertices. Maybe I have a different connected component on this side. And let's say it has a bunch of other. So I cannot say that after I remove my cycle C, my remaining graph is Eulerian. But I can say that every connected component of the remaining graph is Eulerian, right? Because after I remove C, the remaining graph still satisfies the condition that every vertex has even degree. So if I'm doing an inductive proof here, and again, I'm doing induction on the number of edges, I can say, okay, look at this red graph. It's a graph that has even degrees. It's connected. So it should be Eulerian by induction, right? And again, I'm not trying the base case of the induction, just prove the base case for yourself for small values. Okay, great. So now my situation is like this. I have a bunch of connected components, maybe again more than one, and each one of them is Eulerian, and they're also kind of connected to each other by this cycle C. And I want to say that my whole graph is Eulerian. Okay. Now, what can I do? Well, I know that this red part is Eulerian, right? And if this red part is Eulerian, it means that I can start from this vertex, let's call it U, and I can see all of the red part and I can come back to U. So that's my Eulerian circuit in the red part. Okay. The same thing here. This green part is also Eulerian, so I can start from this vertex, let's call it V, see all of the green part and come back to where I start. Okay, so let's just start going around this cycle C. I start here. I first take the edges of the cycle. When I get to U, I do the Eulerian walk on the red part. It covers all of the red part, comes back to U. And then I continue going around my cycle. When I get to the first vertex that is connected to the green part, I do the Eulerian the Eulerian walk on the green part. And then it comes back again to V. And then I can continue this. Again, I do the Eulerian path, I don't know why I say path, Eulerian walk on this side. And then I finally finish the cycle. So I can do this in any case, right? No matter how large my cycle is, I can just start the cycle. I'm going around the cycle C. Every time I see a vertex that was connected to some other component, I just do the Eulerian walk on that component. It starts at this vertex and ends at the same vertex. So then I can continue going around my cycle. So eventually I see each one of the edges exactly once. So my graph is Eulerian. Okay. Now, this is pretty easy. And basically, I'm giving you also an algorithm here, right? So if I give you a graph and I ask you, is this Eulerian or not? You just compute the degree of every vertex. If all of them were even, you say it's Eulerian. And if I ask you for the Eulerian circuit itself, you know how to find it because I just explained how to actually find an Eulerian circuit. Now, a very similar concept is the concept of a Hamiltonian cycle. And a Hamiltonian cycle is a cycle that goes over all vertices. Cycle that visits all vertices of my graph. And of course, because it's a cycle, it's visiting every vertex exactly once. Okay. Now, if I give you a graph and ask you, does this graph have a Hamiltonian cycle? That's a much harder problem. It's actually one of the famous NP-hard problems. So we don't have a polynomial time algorithm. We don't have any fast algorithms to check if a given graph has a Hamiltonian cycle. So this is a situation that happens quite often in graph theory. You have problems that look kind of similar to each other, but one of them is trivial, one of them is super hard. Okay. What else? Okay, I want to prove this theorem, which is actually kind of interesting. I want to say, let G be a graph with M edges. And suppose that I want to make my graph G bipartite. So I want to remove some of the edges so that G becomes a bipartite graph. Okay. I want to say that I can always keep at least half of the edges. So G has a subgraph H with at least half of the edges such that H is bipartite. Let's do it on this example. Let's say this is my graph G. How many edges do I have here? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm saying that there is definitely a subgraph here with at least 5 edges that is also bipartite. Or another way of looking at it is that I can erase at most 5 of the edges to make my graph bipartite. So let's try this. Let's say I erase this edge, I erase this one, and I erase this one. And I claim that this graph is now bipartite. How can I show that? Well, if I can color the vertices with 2 colors such that every edge goes between vertices of different colors, then it's bipartite because I can say one color is one of my parts and the other color is the other part. So let's say I color this one green, I color this one red, this one red. I'll give this one green, this one green. Let's say I remove this one too. 2, 3, 4, okay. And let's say I make this one red and I make this one green. Okay. So now you see that the green part and the red part are a partition of my vertices that prove that the remaining graph is bipartite. Okay. And I removed only 4 edges. So why can I always do this? So again, another way of saying this theorem is that I can color my vertices with 2 colors, red and green, such that most of the edges are going between the parts, going from red to green or from green to red, right? But not in this, they're not in the same part. That's what I want. Okay. So here's the thing. Let's look at all of the subgraphs of G. And for each one of them, let's check if it's bipartite or not. And let's pick the largest subgraph that is actually bipartite. And if there are several largest subgraphs that are bipartite, pick whichever you want. And when I say largest, I mean a subgraph that has the maximum number of edges. Okay, so let H be a graph on the same set of vertices as V, but now I have a different set of edges. I say, let this be a largest bipartite subgraph of G. Okay. I claim that this H definitely has at least half of the edges of G. So my claim is that the number of edges in this graph H is at least half of the number of edges. Okay. But to prove this, I'm just going to look at every vertex. So I have this graph H and it's bipartite, right? So I have some green vertices on one side and I have some red vertices on the other side. And then here in between, I have the edges of H, right? And of course, H is bipartite, so every edge is going between green and red. But then in my original graph in G, I might have some edges like this as well, right? But these were the edges that I basically removed to get H. Now, I'm going to say, look at one particular vertex. Look at this vertex, let's call it V. Okay. Some of the edges going out of V are also in H, and some of them were edges that I had to remove when I went from G to H. Okay. Now, here's the thing about this. I say that for this vertex V, the number of edges that remain in H are greater than or equal to the number of edges that are removed. Okay. Or another way of saying this is that I want to say for every vertex V, the degree of V in H is at least the degree of V in G divided by 2. Okay. Now, suppose this is not the case. So suppose, for example, I have a vertex V here, and its edges were like this. So it had degree 5 in the original graph, but now it has only degree 2 in this bipartite graph. What does this tell you? It tells you that V actually has 3 green neighbors, but it has only 2 red neighbors. So I can just change the color of V, change it to red. Take V, move it to the other side, right? So if I just move V to the other side, what would happen? The number of edges increases. Because if I move V from green to red, I will lose these 2 edges, but I will gain these 3 edges. Okay. But that's contradictory with the definition of H. I said H is the largest bipartite subgraph of G. Or if there are several, it's one of the largest bipartite subgraphs of G. Right? So this should not be possible. And this contradiction shows that the degree of V in H is at least half of the degree of V in G. Okay. But I want to talk about the total number of edges. How can I do that based on the degrees? We had this very simple lemma, which said that in every graph, the sum of the degrees is twice the number of edges, right? So if I take twice the number of edges in H, that's just the sum of the degrees of the vertices in H, right? But we said that the degree of every vertex in H is at least half of its degree in G. So this is going to be greater than or equal to the sum of the degrees in G of the vertices, all of it divided by 2, right? But what is the sum of the degrees of vertices in G? That's twice the number of edges in G. So it's 2m divided by 2. This is just m, right? So I got that 2 times the number of edges in H is greater than or equal to the number of edges in G, which is exactly what I wanted to prove. Now we want to look at something else. If I give you a graph, you can easily write down the sequence of degrees of all the vertices, right? So I did this here, for example. These are the degrees of the vertices in this graph. And let's say that I also write them in a sorted order. Okay, so for this graph, the degree sequence would be 4, 4, 4, 2, 2, 2. Now, suppose someone gives you a sequence and asks you, is there a graph that has exactly these degrees for its vertices? How would you answer that? So this is the question. So given a sequence, let's call it D1, D2 to Dn. And actually, let's say they're really nice, so they're giving you the sequence in sorted order. So D1 less than or equal to D2 to Dn. And let's say that all of these numbers are between 0 and n minus 1, because those are the numbers that can be degrees of vertices in an n vertex graph. So given a sequence of numbers between 0 and n minus 1, the question is there a graph with this degree sequence? Now, the problem is really easy if I say I don't necessarily want simple graphs. So if I allow multiple edges and if I allow loops, then this problem becomes really easy. Okay, so this is my first theorem. I say that this sequence D1 to Dn is the degree sequence of a graph. And here I'm not saying a simple graph of a graph G. So let's say not necessarily simple. If and only if the sum of the di's is even. So one side of this theorem is trivial. If the di's are the degrees of the vertices in a graph, their sum is twice the number of edges in the graph, so their sum has to be even. I'm saying the opposite here, actually, also holds. I'm saying that if I just give you these numbers and their sum is even, you can always form a graph that has exactly these numbers as the degrees of the vertices. Now, why does this hold? First of all, let's look at a very simple case. Let's look at the case where all of these numbers are even. Okay, so let's say, for example, my numbers are 4, 4, 2, 2, 0. I can easily create a graph that has these degrees. So I need a vertex of degree 0. I just put a vertex of degree 0. I need a vertex of degree 2. I put a vertex and I add a self-loop. And this self-loop counts as 2 in the degree of this vertex. Right? So I do the same thing. I need another vertex of degree 2. I need a vertex of degree 4, just add 2 self-loops. And this is 4 at another. So if all of the degrees are even, the problem is very trivial. You can just solve it with loops. Okay. What if not all of the degrees are even? I might have a bunch of degrees that are odd. So I want to first of all make them even. How many odd degrees can I have? An even number of odd degrees, right? Because the sum of the degrees is even anyway. So let's say I just create one vertex for every element in here. So let's say I have whatever 4, 4, 3, 3, 1, 1. Okay. And let me just add a 5 here and a 7 as well. So let's say these are my degrees. I just create one vertex for each one of these degrees. Okay. And then I say, let's create a way of making the odd ones even. How can I do this? I can take two of my odd numbers and I can connect their corresponding vertices. So let's say I take this 7 and I connect it to this 3. Okay. What does this mean? This means that now this 7 is effectively becoming a 6 because I just need to add 6 more edges to this vertex. And this one becomes a 2. Now, again, I pick two other vertices that have odd degrees and I connect them. So this one becomes 0, this one becomes 4. And then I connect this 3 and 1. This one becomes 2, this one becomes 0. Okay. I can always do this. I can always pair up my odd degree vertices because I have an even number of odd degree vertices because the sum of all the degrees was even. Okay. And after I do this, I will only have even numbers and I know how to solve it for even numbers, just add self loops. Okay. So I'll just add a self loop here for this 2. I add a self loop here for this one. I add 2 self loops here. I add 2 loops here, 2 loops here. And then I will need actually 3 loops here. This is my graph. Okay. And of course, this algorithm works for any sequence as long as the sum of the numbers is even. So a sequence is a degree sequence of a graph if and only if the sum of the DIs is. But this is too simple, and we like to make our lives harder. So the question is, what if I don't allow self loops? And what if I don't allow multiple edges either? So what if I want it to be a simple graph? Okay. So we say that a sequence is graphic. That's really the name that they went with. D1 to Dn is graphic if it's the degree sequence of a simple graph. Now for this, I'm going to give you an algorithm. I can't just give you a very simple mathematical thing to check, like whether something is odd or even, but I'm going to give you an algorithm. So let's just do an example first. Let's do this example of 4, 4, 2, 2. What's this graph? Oh, I had 3 4s and 3 2s. Okay. So let's just look at this degree sequence. Okay. Here's what I'm going to do. I say that I need a vertex of degree 4, and this is my highest degree. So I'm going to again create one vertex for each one of these degrees in this sequence. And I'm going to take this first one, and I know that it should have a degree of 4. So I'm just going to connect it to the next 4 vertices. Okay. So I'm going to say connect this one to this one, this one, this one, and this one. Okay. So now this vertex has a degree of 4. I don't need to consider it anymore. But now I have to add 3 more edges for this vertex, 3 more edges for this vertex, 1 edge for this one, and 1 edge for this one. Okay. And I keep doing the same thing. Every time I pick a vertex with the highest degree, highest remaining degree, and I add edges between that vertex and all the other vertices of the highest remaining degree. Okay, so here I have to add 3 edges to this vertex. And well, I have a 3 here, a 2 here, so I connect it to this 3, I connect it to this 2, and then I have to also connect it to one of the ones. So let's say, connect it to this one too. This comes to this one. And now finally here, I have this vertex that needs 2 more edges, and I have 2 other vertices that need 1 more edge. So I connect this to those 2 as well. This becomes 0, this becomes 0. Okay. So this is my algorithm. It's a greedy algorithm. Basically, it says every time pick a vertex that needs the maximum number of edges to be added to it and connect it to other vertices that need the maximum number of edges. Okay, great. So first of all, if this algorithm works, then definitely my sequence is graphic because I'm creating the graph, right? So if the algorithm succeeds, if I can go over all the sequence and I create the graph and I make all the numbers 0, then the sequence was a graphic sequence. But what's interesting is that the opposite also works. And by the way, this is called the Havel-Hakimi algorithm. So this is our theorem. Basically, my theorem is that a sequence is a graphic sequence if and only if the Havel-Hakimi algorithm succeeds in creating a graph, right? But if I want to write it a bit more mathematically, I say it like this. I say a sequence, let's call it D1 less than or equal to D2, so on to Dn, is graphic if and only if, well, what is the operation that I'm talking about? I'm saying take the vertex with the highest degree Dn and connect it to all of the previous ones. So if and only if I remove Dn and I will have Dn minus 1 minus 1, right? I will have Dn minus 2 minus 1. These degrees all decrease by 1. Up until Dn minus Dn minus 1, right? And before that, I will have the same degrees. So D1, D2, so on. So the last Dn numbers are decreased by 1. Every other number remains the same. If this sequence is graphic, then my original sequence is also graphic. And by the way, in my original sequence, I'm saying that these are written in a sorted order, but here I'm not saying that because when I do the minus 1, maybe then I have to sort them again. Right. Okay. Now, again, one side of this theorem is trivial. If this second sequence is graphic, then the first sequence is also graphic because just do the algorithm, right? So if the second sequence is graphic, I have a graph with n minus 1 vertices and these degrees. And if I just add my nth vertex and I just connect it to the last dn vertices in the previous graph, I get a graph with this sequence. Okay, so one side is trivial, the other side is what we have to prove. So what is the other side? The other side is if, let's give this sequences some name. Let's call this one A, let's call this one B. So it's trivial that if B is graphic, then A is graphic, but I want to prove that if A is graphic, then B is graphic. And oh, by the way, I'm also assuming that n here is, let's say, at least 2 or 3. Just the base cases, check it on. Okay. But here's the thing. If my sequence A is graphic, it might be that I have a graph with degree sequence A, and it might not look like the graph that was created from this algorithm at all, right? So I want to take that graph. I want to say, suppose someone else gave me a graph that has the degree sequence A. I'm going to change it until it looks like the output of this algorithm, until it looks like the graph that this algorithm creates. Okay. So here's the thing. Let's say I have, again, D1, D2, so on, Dn minus 1, Dn. This was my sequence A, right? So let's say someone has given me a graph with this degree sequence. Let G be a simple graph with degree sequence A. Okay. What does this mean? Well, of course, G is going to have a vertex of degree Dn. It's going to have a vertex of degree Dn minus 1 and so on. Let's number the vertices based on the degrees. So let's say that I just number the vertices in G such that vertex 1 has degree D1, vertex 2 has degree D2, and so on. So look at vertex n. It has degree Dn. There are Dn edges going out of n. But my problem is that if I use the Havel-Hakimi algorithm, these edges that are going out should go to n minus 1, n minus 2, so on, to n minus dn. Basically, those should be the neighbors of n if I use the Havel-Hakimi algorithm. But maybe that's not the case. Maybe n is connected to somewhere else. Okay. So I can do this. I can say, let's look at n. And let's say that there are some neighbors of n in this graph. Okay. So these are all the vertices that n is connected to. And then I have a different set, which is the set of vertices that I wish n was connected to. Right? So I have this other set. And let's say this set consists of the vertex n minus 1, n minus 2, so on, to n minus dn. So I wish that n were connected to these blue vertices, but n is unfortunately connected to the red vertices. Right? Now I want to somehow change the graph so that n is connected to the blue vertices, but the degrees of all the vertices remain the same. Now, in some cases, I'm lucky. Some vertices might be both in the red set and the blue set. I let them be. But I can always take a vertex from the red set, let's call this one U, and I can take a vertex from the blue set. Let's call this one V. Okay. I want to add the edge from N to V, and I want to remove the edge from N to U. But what is the problem here? The problem is that if I add this black edge, and if I remove this red edge, the degree of N remains the same, but the degree of V increases, and the degree of U decreases. So my degree sequence changes. So in order to do this, I have to find another vertex that is connected to V, but not connected to U, right? And then I should do this. I should basically remove these two red edges, this red edge and this one, and add the black edges. And if I do that, then the degree of every vertex remains the same, but I'm one step closer to having my favorite set as the neighbors of n. Okay, so this is called the two switch. Basically, I want to find something like this. I want to find n, and let's say red is the edges in G. I want n to be connected to some vertex U, and I want there to also be a vertex V where n is not connected to, and I want to add this edge. And then I want there to be another vertex, let's call it W, where W is not connected to U, but it is connected to V. So basically, I want to find a situation like this. I want to find three vertices, U, V, and W, such that n is not connected to U, such that n is connected to U, but not connected to V. So basically, the red ones are the edges in G, and the black ones are the edges that I want to add, right? So this operation is called the two-switch. And if I can do this, if I can find such U, V, and W, and if U is one of the undesirable neighbors that I don't want to be neighbors of N, and V is one of the desired vertices that I want as neighbors of N, then I'm getting one step closer to having the correct set of neighbors for N. Okay. Why can I always find such a W? Because look, if I start with N, of course, I can find U and V. If I cannot find U and V, that means that the red set is the same as the blue set. So I have exactly the same set of neighbors that I wanted. There's nothing to do. I'm happy, right? So the fact that I can find U and V is trivial. But why can I always find W? So what is W? W is any vertex that is a neighbor of V, but not a neighbor of U, right? But here's the thing. Which one has a higher degree, V or U? V has a higher degree than U. So there is definitely a neighbor of V that is not a neighbor of U, right? What if they have the same degree? Yeah, if they have the same degree, then it means that the two sets are already the same, right? Because I can always take the vertex with the smallest degree from the red side and the vertex with the highest degree from the blue side. So they never have the same degree. And so the degree of V is more than the degree of U. So V definitely has a neighbor that is not a neighbor of U. I call that W. And then I do this two switch. And when I do this, well, the difference, the size of the difference of red and blue is shrinking. So I cannot do this forever. At some point, red and blue will become the same. And that's great because now I found a graph that matches the first step of my algorithm, right? It matches this idea that I take the vertex with the highest degree and I connect it to all of the next vertices in the order of degree, right? And it also has the same sequence of degrees. Now I can keep doing the same thing. So I can now do this for the second step of my algorithm, third step of my algorithm, and so on. Basically, if anyone gives me a graph G that has this degree sequence A, I can turn it to the graph that will be created by the Havel-Hakimi algorithm. So a sequence is graphic if and only if the Havel-Hakimi algorithm succeeds in creating a graph. Great. Now I want to prove some other things about trees. So we've already seen three equivalent ways of defining trees. Basically, we had these three properties, connectedness, lack of cycles, and having n-1 edges. And we've seen that any graph that has two of them definitely has the third property as well. So we have three different ways of defining what a tree is. Now, I want to prove another theorem. I want to say that the graph G is a tree if and only if there is a unique path between every pair of vertices. Again, this kind of makes intuitive sense because if you look at a tree, so let's say this is my tree, between every pair of vertices, there should be only one way of going, for example, from here to here. Right? But we want to prove this. So let's first do the first side. So if G is a tree, what does that tell us? So G is a tree. It basically gives me all the three properties. It says that it's connected, it has no cycles, and it has n-1 edges. So I can use any of these. Okay. I want to say there is a unique path between every pair of vertices. So first of all, since my graph is connected, there is at least one path between every pair of vertices. So if I give you the vertices u and v, there has to be a path between u and v because it's connected. So what I have to prove is that there cannot be more than one path. So let's try to prove this by contradiction. Suppose there are two paths between u and v. Suppose, let's say P1 and P2 are both UV paths. So they're paths from U to V. And they're not the same. What does this tell you? Cycle, yes. Well, we have to be a little bit careful about this because I have U here, I have V, and I have two paths, right? So let's say I have this path. This is P1. And I don't have the assumption that these paths are disjoint. So maybe I have another path. This is, let's say, P2. Let me use a different color, actually. So maybe this is P2, and maybe it shares some parts of P1. Right? But I have two different paths between U and V. But if this is the case, then I can just put these two paths together. So start from U, take P1, go to V, and then take P2, go back to U. This is going to give me a closed walk. And we've already seen that every closed walk includes a cycle. So there's definitely going to be a cycle, but the cycle is not necessarily all of P1 and P2. In this case, for example, there is a cycle here and there is a different cycle, right? But there is definitely a cycle. But if there is a cycle, then it's no longer a tree because the definition of tree was that there's no cycle. Okay? So this leads to a cycle. This gives a closed UV walk. Okay. And therefore a cycle. So the cycle is not necessarily containing both U and V. Again, as you can see here, I have a cycle on this side. I just know that I have a cycle. And this is a contradiction with it being a tree. So what we've proven so far is that if G is a tree, then there is a unique path between every pair of vertices. Now I want to prove the other side. So suppose that there is a unique path between every pair of vertices. I want to prove that my graph is a tree. First of all, my graph is connected. Because from every vertex U to every vertex V, there is a unique path, so there is a path. So it's connected. Okay. So G is connected. Right. Because there is a path between every pair of vertices. Now I need to prove one more of these two properties to show that it's a tree, right? It's quite hard to say it's it has n-1 edges, but it's actually easy to show that it has no cycles, right? So why can't G have a cycle? Let's prove that by contradiction. Okay, so I want to say G has no cycles. I say suppose C is a cycle in G. Okay, so I have, let's say, this cycle in G. Just take any two vertices in this cycle. Let's say I take vertex U and vertex V. There are two paths between U and V. You can go clockwise or you can go counterclockwise. Right? So if C is a cycle, there are at least two paths. Maybe there's even more, but I know that there are at least two paths between U and V. this is a contradiction because our assumption was that there is exactly one path. There is a unique path between every pair of vertices. So this shows that my graph cannot have a cycle. But if I have a graph that is connected and has no cycles, it's a tree. So now we have a fourth way of defining trees. I can just use this as the definition of a tree. I can say G is a tree if there is a unique path between every pair of vertices. I'm going to give you another way of defining trees. So suppose I have a tree. So look at this tree. Can I say that all the vertices in this tree are cuts? No, because the leaves are not cuts, right? So if I remove this vertex, for example, I will still have one connected component. But I can say that every vertex other than the leaves is a cut. Right? But that's not so satisfying because I cannot say anything about all the vertices. I cannot say all of the vertices are cuts. But can I say this about the edges? Can I say all the edges are cuts? Intuitively, it makes sense that if I have a tree and if I take one edge and let's say I take this edge and I slice up the tree by removing this edge, I should get two connected components on the two sides, right? So I want to say that this is another property that really defines trees. So I want to say this. I want to say a connected graph G is a tree if and only if all edges of G are cuts. So basically, this is telling you that another way of defining a tree is that it's connected and all of its edges are cuts. Okay, let's do this. Let's do this side first. So suppose that G is a tree. And I want to take some edge in G, and I want to say that this edge is a cut. So let's say E is an edge in G. I can assume that this edge connects two vertices and then just give them some name. So I say this edge is connecting U to V. Based on the previous theorem, since G is a tree, there is a unique path between U and V. So that unique path is just the edge E. So if I remove E, there is no longer a path between U and V by the previous theorem, because there was only one path and I removed it. So if I remove E, U and V will no longer be in the same connected component because there is no path between them. So E is a cut. Okay. So there is only one path between U and V. And this one path is E. So removing E disconnects U from V. So E is a cut. Okay. So far, I've proven that if I have a tree, every edge in that tree is a cut. Now I have to prove the opposite side. I want to say that I have a connected graph and all of the edges of my graph are cuts. So I want to prove that it's a tree. So this side is that G is connected and all edges are cuts. So for any one of the edges, if I remove it, my graph will no longer be connected. Okay. Again, going back to our definition of trees, we said that we need to prove two of these properties and it will always have the third one. I already have the assumption that it's connected. I want to prove there is no cycle. If I prove there is no cycle, I've proven that it's a tree. Okay. So let's prove G has no cycle. But we had this other theorem, if you remember, which told us when an edge is a cut. There was this theorem that said an edge is a cut if and only if it is not part of any cycle. Right? So I'm saying that all of my edges are cuts. If all of my edges are cuts, it means that none of my edges appear in any cycle. So I cannot have any cycle at all, because every cycle will have to have some edges, right? So all edges are cuts. Therefore, no edge appears in a cycle. Therefore, there is no cycle. But instead of using that theorem, I could just do the argument that we did in the proof of that theorem pretty much. So at this point, this theorem is proven, but we relied on that previous theorem to do this. But let's just try to do it without directly relying on that previous theorem. So I have a graph G, it's connected, all of its edges are cuts. I want to say it has no cycle. I say, let's try to prove this by contradiction. So this is proof 2. Suppose C is a cycle in G. Okay. So I have this cycle C. Now consider one of the edges in this cycle, whichever you want. If I remove this edge, the connected components are not going to change because the two endpoints are still connected from the other side of the cycle. So this edge cannot possibly be a cut. But I have the assumption that every edge is a cut. So this is a contradiction. This shows that I cannot have a cycle. Now I want to prove another theorem, which is honestly kind of trivial, but it sets the stage for what we want to do later. So I want to say every connected graph G has a subgraph T and let's say that this G is VE, and let's say that this subgraph has the same set of vertices, so T, but has different edges, such that T is a tree. So this is actually called a spanning tree. What I'm saying here is that if I give you any connected graph G, there is a subgraph that has all of the vertices, but not necessarily all of the edges. So it's obtained by removing some of the edges. And it's a tree. So every connected graph contains in it at least one tree that connects all of its vertices together. Okay. And I'm not saying this T is unique. You might have many such T's, but there is at least one. Why is this the case? Now, we can give many different proofs of this. I can give a constructive proof. I can give an extremal proof. Let's see. Let's see if I can use this previous theorem, for example. So I know that a connected graph is a tree if and only if all of the edges are cuts. Okay. So I have this graph G. I first check which edges are cuts. If all the edges are cuts, then G is already a tree. So I would just say T is the same as G. Otherwise, I have at least one edge that is not a cut. I remove that edge. And by definition, since it's not a cut, my graph remains connected, right? So now I have a smaller graph that satisfies the conditions of the theorem. So I can continue this and I can prove this by induction. Basically, suppose that I'm doing induction on the number of edges, right? So I'm saying that this is a connected graph. So it's going to have at least n minus 1 edges. We've proven this before. If it has exactly n minus 1 edges, then it's a tree. If it has more than n minus 1 edges, there is an edge that is not a cut. Remove that. And then just use induction hypothesis. Okay. But I can also have another way. Here's another way of proving this. I say start from a vertex. Let's call this V. And just look at all the neighbors of V. So I have a bunch of vertices that are neighbors of V. And keep the edges from V to its neighbors. Okay. And then look at the neighbors of V. So all the vertices that can be reached from V using 2 edges. Okay. I'll put them here. Now, some of them might already be neighbors of V. I'm going to ignore that. So if I have something like this, I have a vertex that can be reached by 1 edge or by 2 edges, I will always reach it by 1 edge. Okay. Now, so these are the vertices that can be reached by 1 edge. These are the vertices that cannot be reached by 1 edge, but can be reached by 2 edges. Okay. So each of these vertices should be connected to some of the vertices in the previous layer, maybe to more than one. Just keep one of those connections. I don't care which one you keep. Okay, because I want this to be a tree. So if this is connected to this one and this one, just keep one of them. Okay. And then continue this. Find the vertices that can be reached from your original vertex with 3 edges. And each of them should be connected to exactly one of the vertices that could be reached with 2 edges. Again, if you have more than one connection, just remove the extra ones, keep only one, and so on. If I continue this process, I will eventually have all of my vertices added to this tree, right? Because if I have any vertex, it's a connected graph. So I can look at the distance from V to that vertex, and the distance is the length of the shortest path. Okay, so let's say I have a vertex that is at distance D. So the shortest path from V to that vertex takes D edges. It will be added to layer D of this tree. And it's a tree because every vertex in layer D is connected to exactly one vertex in layer D minus 1. Okay, so how would you prove that this is a tree? You can just check that it has the properties of the tree. You need to check 2 of the properties, but actually it's very easy to check that it has all 3 properties. So first of all, it's definitely connected because every time, I mean, all of these are connected to V eventually, right? So it's a connected graph. It has n minus 1 edges because when I'm adding V, I'm not adding any edge. But whenever I'm adding any other vertex, I'm adding 1 edge, which connects this vertex to the previous layer. So I have n minus 1 edges. It doesn't have any cycles either. How do you prove this doesn't have any cycles? Yes, so suppose there is a cycle. What would that tell you? So every vertex that is at level D can only be connected to vertices in D minus 1 and D minus 2. And it's connected to only one vertex in level D minus 1. Okay, but if I have a cycle, let's say this is vertex D. Let's say this is D minus 1. This should be at level D plus 1, right? What is the level of this vertex? It has to be D plus 2 because this vertex at level D plus 1 can be connected to only one vertex of level D. Okay. Now continue the cycle. What is the level of this vertex? D plus 3. As I'm continuing, the level is going up. It will never go back to D minus 1. I cannot close this cycle. So I cannot have a cycle.